Hi everyone, and welcome to the second SOLARX webinar. Today we have the pleasure to have the SOLARX partners that will speak about the technical and social aspects of an innovative dispatchable concentrated solar power. First of all, I would like to do some housekeeping. For you to know, this event will be recorded and will be shared on the SOLARX media channels during the Women in Science Day, which will be on 11th of February. And I wanted to also mention that you can use the chat box in case you are experiencing any technical difficulties. So we will try to fix them as soon as possible. And also, by the end of the session, we'll have a panel discussion. So you can already use the Q&A function, and there you can submit if you have any questions or topics that you would like to be mentioned by the end. I think that our speakers will be more than happy to answer. So I will not extend myself more. I want to introduce the speakers that we will have today. Myself, I am Miriam Frances from Accelopment, and I am organizing this webinar together, in this case, with Marta Murkowska from EMD International, who will give us an overview of the SOLARX project, and later Maitane Ferreres from Fraunhofer ISE will follow, explaining the solar field design and optimized aiming strategies. Later on, Rola Elvillo from ACCIONA Industrial will explain the advancing hydrogen generation with CCUS. And finally, from DTU University, the Technical University of Denmark, we have two speakers. First of all, Megha Gupta, who will explain the modeling and operation of SOLARX 2X plants. And afterwards, Ode will continue with the quantitative sustainability considerations of SOLARX. As I said, we'll have a panel discussion in the end. So if any of you have any questions or topic that want to mention, please feel free, because our speakers will be happy to answer. So all said, Marta, now the screen is yours. Please go ahead and start with your presentation.
Thank you. Yes, I'm going to share my screen now. This one. And thank you, Miriam, for organizing this event. I think it's great that we are having something like this for the Women in Science Week. Can you see my screen now?
Yes.
Perfect.
Perfectly.
Yes, so as Miriam mentioned, I'm going to give a short introduction to what is the SOLARX project. The SOLARX project is about a dispatchable concentrated solar to X energy solution for high penetration of renewable energy. We are funded by the Horizon Europe program, and our project has a duration of 3 years, is led by Jeddah University, and we have 9 partners from 7 different countries in the project. The coordinator is Jeddah University, and the remaining partners are Higir, ACCIONA, EMD International, where I am employed, and Fraunhofer Institute for Solar Energy System, Danish Technical University, University of Sherbrooke, which is also CNRS, and Cyprus Institute and accelopment in Switzerland. In the context of the project and why we are proceeding with the project, it's something that many researchers and many industries are actually talking about and working with. It's that in order to, in the future energy systems, also as we can see here from the International Energy Agency, we are talking about a way higher penetration of renewables. We are aiming at decreasing the CO2 emissions, ideally net zero emissions by 2050. And in all of these scenarios, we are talking about a high increase in the penetration of renewables, as we can see in the figures here. And the problems that we'll be facing is that on the way to this 100% renewable energy systems, we'll be going away from the old world, as we called it here, where we were talking about having a base load and peak units that will take these variations throughout the days. We will be switching to a completely new world when we have the variable renewables working around the clock. And then on top of that, we'll have to have dispatchable renewables. And this is something that we are working on in this project. We are working with a dispatchable renewable system, which will be able to address the issues in the new world in the future. The concept of the project, it's, as you can see, quite complex, but we will start from here. I will just use my pointer. So first of all, we have the solar field. That is these mirrors installed next to the tower. We have here the Fraunhofer Institute working on the aiming strategies for the mirrors, and Miriam is also going to explain that in her presentation in more details. Here we have a smart energy management, including artificial intelligence, and the aim is to increase the ROI by 30%. These mirrors, what they are doing, maybe also in the same topic, we have this continuous monitoring system. That is something that we included in the project a little bit later. This is a way of monitoring if the performance of the aiming strategies is correct, and also monitor the field optical efficiency, feedback to the optimization. And that is something that we will also work on that in that project now, where we talk about how this could be implemented and tested to optimize the whole solar field. The solar field is aiming at the tower, and in the tower we have 3 different receivers. We have the efficient concentrated photovoltaic receiver here, and this is something that the Jena University is working with. Additionally, we have a hydrogen receiver, which is producing hydrogen from biogas reforming. And this is something that Rola will touch upon in the presentation later on. And then we have a concentrated solar thermal receiver, this is a more established technology that we included here also for the sake of analysis. All of these energy vectors, we are going to be modeling how these can be used in different contexts. So we are talking about different end users of this system. This can be mainly industrial customers, perhaps a standalone plant. Of course, we will analyze different demands, different electricity demands, hydrogen demands, heat demands. And this analysis is something that we are doing together. So EMD and DTU, we are doing this optimization and analysis of how we can ideally optimize this system and use this system in real life. And last but not least, we have also the big topic of techno-economic and environmental and social assessment, which the environmental and social assessment is something that Out will be presenting as well today. A little bit more details. The key technological elements that we defined is the smart solar resource management. As I mentioned already, I will not go into these details, but you're welcome to also have a look at the presentation later on. We have the other key technological element, which is the concentrated photovoltaic dense array receiver. We are aiming at a very high efficiency of this receiver, cell efficiency of 45.9%, and the system efficiency then reaching around 41%. And we also have a bi-energy hydrogen receiver. This is the receiver that will directly, using the energy from the sun reflected by the solar field, will directly reform biogas into syngas, which has a very high content of hydrogen in it. And this is also something that, and also we will integrate carbon capture, which is what Rola will touch upon later. The objectives of this project is basically to demonstrate the technical and economical reliability of this solution at the laboratory scale, we want to develop the high efficiency CPV receiver, develop the hydrogen receiver, and of course disseminate the results, while also having the whole aspect of socio-economic development included as well. And EMD and DTU are working towards the future integration of the system and the cases where we could be using the SOLARX development. Of course, as in all the projects, we are facing challenges, and these are mainly based on the technical aspect of it. So reaching the desired efficiency of both the CPV and the hydrogen receiver, finding the correct solar resource management system that will allow for the best optimized performance of the plant. And we will aim at creating a roadmap towards system integration and how to commercialize this technology in the future. I will not take much more of the time. It's also because we have a lot of very interesting technical presentations coming. But here are the main contacts, the SOLARX coordinator, Jerome, and Miriam, who is present here in the call, that you are always welcome to reach out. You are also always welcome to reach out to us, the presenters. And now I'm giving the word to Maitane, and she will be presenting the topic of solar field design and optimized aiming strategies. I will stop sharing my screen.
Thank you, Marta. I will share my screen now. Can you see it?
Yes.
Yep. Okay. Nice. So yeah, in this presentation, I will focus, as Marta said, in the solar field. She already explained that we have 3 receivers, and our aim is to be able to meet the optimum distribution of the solar resource depending on the demands that we have of electricity, heat, or hydrogen. And additionally, since the requirement of each receiver, they are also very different, we need to have different aimings within a receiver. And on the contrary to the thermal, the hydrogen or the CPV require a more uniform flood. So I will present how we are making the design of the heliostat field to meet the requirements, and then also the solar management algorithm that we are developing to obtain these distribute aimings. Let's focus first on the design of the field. So we want to have the most possible compact distribution of the heliostats in our field, while we also want to avoid shading and blocking. And for this, imagine that we have 2 heliostats here, O and G. What we do is projecting the shadows. We can go from a 3D problem to a 2D problem. And yeah, so this is the starting point of our method. So what happens is that the sun is moving. So we don't have a single projection of the shadow. So what we do is we have several sun positions in the sky, and we project the vectors to calculate all the shadows, and then we weight the shadows with the DNI, and like this we create somehow like a shading field. And then we take the percentile that can be an input that can vary, and with this percentile we define the contour of the shadowing. And we do the same, but with the aiming point for the projection for the blocking. And once we have the shadows, we implement a simulation using PyMock and Pygame, and the shadows, they create a boundary on the space to ensure there is no overlap, and then the heliostats are attracted to the middle with artificial gravity. So the middle would be the aim point. And like this, we also can have multiple aim points, but here you can see the implementation for a surrounding field with an area constraint. And here you can see how how the helios are attracted to the center while keeping their shadows, and we can see how the shading. So the shading is the green shadow, it's predominant in the center, and then once we go farther, the blocking shadow, which is in orange, is predominant. And like this, we can create this kind of heliostat fields that are optimized within the space. And once we have the heliostat field, we need to have an optical model that is able to calculate the different flux distributions into the receivers. And for that, we set a combination of shares that can go in the different receivers that goes from 0 to 100 with the steps of 10%. And also we need to make a sky discretization to calculate all these possible shares for different sun positions. And like this, at the end, we have a very big database with all these possibilities, and then we can interpolate between them to calculate the share that we have in this moment, and we calculate the flux also with the DNA that we have in this moment. And to create this database of different shares, what we do is first we make a ray tracing simulation with our optimized heliostat field design, and we perform a ray tracing simulation for each receiver, and then we extract the contribution of the single heliostats in the receivers, and like this we can define the ratio as we want. And here we create different ratios for the heliostat field. But then also, as I said in the beginning, we also need to optimize the aiming distribution in the CPV and the hydrogen receiver. And for this, we also use this single heliostat contribution. And having defined the requirements and limitations that we have for the receivers, we have a meta-heuristic algorithm that can distribute the aimings. And then what we do is we shift the flux, and then like this we can create a more distributed aiming. And here, for example, you have an example of 1 square meter CPV receiver where we created different aimings. So here would be with 4 aimings, and then here also with a more distributed aiming. And so that was my part from the solar management part. I will thank you for your attention. I will be happy to answer any question if you have afterwards. And now I leave the floor to Rola Elbiju from ACCIONA to talk about hydrogen. And I will stop sharing.
Thank you very much, Maitani. I will share my screen. Second, no. Do you see my screen? Oh, wait, not yet. Now, is it in presentation mode?
Yes.
Yeah. Okay. Thank you very much. Okay. So thank you, Maitani, for the introduction. I'll introduce myself very quickly. My name is Rola Elbiju, and I'm an research and development engineer here at ACCIONA. And I specialize mostly in carbon capture. So that's what I'm here to talk to you about today. Sorry. Marta did a very good job explaining the project, so I'm not going to go in much detail. The only thing that I wanted to focus on is that the objective of the project is to be able to produce heat, electricity, and hydrogen from solar energy, to be able to meet the energy demands and be flexible enough to this market. So my role here is to make sure the hydrogen production remains sustainable by integrating a carbon capture solution in the hydrogen production. Okay, So first, let's talk about the hydrogen production. Currently, more than 95% of the hydrogen produced is done through steam methane reforming, which requires very high temperatures and burns 40% of the process gas. So, and it also has an efficiency below 70%. So it's not considered a very sustainable way to produce hydrogen. A new or relatively new technology to produce hydrogen is electrolysis. It's been gaining a lot of interest lately and a lot of research. However, electrolysis remains 3 times more expensive than methane reforming, and its efficiency is even below than 70%, ranging into 50 and 60%. So, and if we want to use solar photovoltaic electricity for electrolysis, we even lower the efficiency to 15 to 25%. So our objective here was to continue using steam methane reforming, but taking advantage of solar energy. And so it's a solar driven steam methane reforming. It has 85% efficiency and we can reduce emissions. So why do we need carbon capture here? Well, we need to capture the carbon dioxide from the methane reforming, and this way we can enable either a carbon neutral or negative hydrogen, and we support global decarbonization efforts. So this system, it's a solar powered microreactor that basically uses, as you can see, I don't know if I have my pointer. Yes. Okay, so it uses solar power, and you have these little reactors. That's why called microreactors, and they're used for methane reforming. Okay, so this system can operate either using natural gas, and then that would be considered blue hydrogen, or biogas, which is what we're focused on mostly here. So it would be considered green hydrogen. Both of these require carbon capture, so we can mitigate the carbon dioxide emissions. Okay, so in the steam methane reforming, it uses methane, so biogas in this sense, and steam. And then we're also taking into account dry methane reforming, which is without steam, and we can also use carbon dioxide from industrial processes. Okay, so I'm going to show you just a little bit the differences between both approaches. I have here the flow diagrams of both technologies. In the first one, hydrogen one, this is where we're considering dry methane reforming, and in this case we use biogas as feedstock. We produce syngas, and then in this case, we require higher temperatures than steam methane reformer, and we achieve lower hydrogen production, but we do use carbon dioxide as a reactant, so that means we can reduce our carbon dioxide emissions. Okay, in the case of the steam methane reforming, we also use biogas as feedstock, but we also use steam, which is water. It produces hydrogen and carbon monoxide, but with a higher hydrogen yield. It requires lower temperatures than the dry methane reforming, but we do need water. So if we need water, we need more resources, and its disadvantage is that it generates more carbon dioxide emissions compared to dry methane reforming. Okay, so both processes, in this case, as you see in the flow diagrams here, we would have to include carbon separation in 2 stages. First, because the biogas has a high concentration of carbon dioxide, so we need to adjust the ratio of hydrogen to carbon dioxide to what we need for the reforming stages. And then also, after the hydrogen is produced, to purify the hydrogen, we would need to separate it from carbon dioxide. So why is it very important to choose the right carbon capture technology? as I said before, we do require two separate steps, and each step requires different different specifications of purity of carbon dioxide, has different pressures and efficiencies, and it's important to adjust these technologies to the requirements to allow a better efficiency and cost. Okay, so this is work that we're doing still. So we are trying to evaluate the different technologies that can be applied in each of the cases, depending if it's steam methane reforming or dry methane reforming, and then as well as the step included if it's the pre-reforming or the post-reforming. Okay, so far the technologies we've been evaluating are membranes, amines, pressure swing adsorption, and cryogenic separations. Okay, in the step, the preforming step, membrane separation could be a very good option because it's very selective to remove carbon dioxide from biogas, and it maintains a good hydrogen to methane balance. For pressure swing adsorption, it's very good for gas separations at low pressures, which is the case in the pre-reforming. And then the cryogenic separation, it's suitable for large-scale carbon dioxide removal when we need high purity carbon dioxide. Okay, and then for the post-reforming step, amine scrubbing would be a very good option since it's a very mature technology, and it's ideal for large volumes of carbon dioxide, mostly in steam methane reforming. Calcium looping could be an option. This is a more innovative approach, but if we have high temperatures of carbon capture, we could take advantage of this heat, and we can make it useful for streams that are concentrated in carbon dioxide, which is biogas is an example of that. And finally, just as I explained before, the cryogenic distillation gives us a good high purity carbon dioxide. And in this case, since the post-reforming stage, if we are considering the utilization of carbon dioxide in another in any other use, the purity of carbon dioxide is a very important thing to consider. So just to resume a little bit, these technologies that I just explained to you, we can see in which step they're better applied, what efficiency they have, what carbon dioxide purity they would give us, and the energy requirements they require. As we see, the amine scrubbing and the cryogenic separation have high energy requirements, and their technology readiness level, the TRL. So I also I thought it was very important to look ahead at maybe future carbon dioxide technologies and innovations that are maybe they haven't reached the high enough TRL to be applied in industrial levels, but since we are evaluating a very innovative technology, I thought it would be important to also take into account the emerging capture technologies. One of which is the MOFs, which are metal organic frameworks. They are highly selective materials, and they require low energy input for carbon dioxide capture. In this case, it would make sense for them to be used for low pressure applications. So in the pre-reforming stage. And then, as I said, calcium looping I mentioned before, but it's very high efficient, and it's good for any applications where we want to use the carbon dioxide, because it would lead to a pure carbon dioxide. And it's best for processes that have high temperatures, because you need high temperatures in calcium looping. And then, so it could be good in the pre-reforming stage. We also have electrochemical capture. So this would be renewably powered. We don't need any heat, and it's best for low carbon dioxide concentrations. Cryogenic separations, we already mentioned this before. It's good because it does not have any chemicals, and it would give us a high purity carbon dioxide, and it's best used in high pressure carbon dioxide steams. And finally, carbon dioxide mineralization. This would be a good approach if we are considering storage of the carbon dioxide. So this would be permanent storage of the carbon dioxide, which is a potential revenue, and also gives us it's a good option for biogas based systems. So I'm done with my technical part. I just wanted to take this opportunity to congratulate all women and girls in science. As a woman in engineering, I do believe that diverse teams lead to better innovation. We're still very underrepresented in STEM, so increasing this number is essential to solving challenges just like carbon capture, climate change, and energy transitions. So I just want to congratulate and celebrate all the women in STEM, especially my female colleagues in the SOLARX project. And to conclude, I'd like to introduce my colleague, Megha Gupta. She's a postdoc research at Technical University of Denmark. She will share insights on modeling and operation of solar-to-X plants. I'm sure you're going to find her presentation very insightful and inspiring. Megha, I'll give you the microphone.
Can you see my screen now?
Yes.
Yeah. Okay. Thanks, Rula, and thanks, Martha, for the nice introduction of this project. It has made my job easier to directly dive into the topic. And so at DTU, we are working on modeling and operation of these solar-to-X facilities and plants. Just for a brief introduction of what we do. So as my colleagues have already explained, that SOLARX integrates 3 different solar technologies to produce different energy vectors and with the aim of having the higher efficiency of conversions. So this system can deliver electricity, heat, and green hydrogen or syngas in a carbon neutral manner. And from a plant owner perspective, if I am building up this kind of a facility, what would I aim for? So the aim could be to maximize the revenue generation while accounting for investments, as we are assuming that these all commodities are linked to their respective markets, and we have the end users who are ready to buy these commodities at different prices at the different locations. So we are trying to integrate these all energy vectors with their corresponding markets to see how we can maximize the revenues from them, and while also accounting for the corresponding capital investments and the operational cost which occurs during the operation of these plants throughout the lifetime. So if we look at the different components of these facilities, so we are dealing with the 4 types of energies, 4 forms of energies, which is solar, thermal, electrical, and chemical. So solar energy is basically captured by the field of heliostats. Thermal energy is basically collected by the CSPs, which are concentrated solar thermal receivers, and then they can be stored in the molten storage tanks, which is a long-term solution, efficient long-term solution. And then the electrical energy, it is produced directly by the CPV in this facility, or it can be also indirectly produced by steam turbine using heat. And then we have the chemical energy, which is basically involved with the production of hydrogen through different processes. So the objective of this task, which we are doing at DTU together with EMD also, so the objective is to manage the production of these different energy vectors synergistically, and to decide which energy vector should be produced at what time of the day, which is more profitable, and then assessing the technical and economical feasibility of this kind of facility. So coming to the operation of these plants, it is very much similar to what Martha has also presented as an overview picture of this whole SOLARX facility. So let me use my pointer. So it is basically consisting of the solar fields, and then we have a solar tower where we have 3 receivers. One is CPV, which is directly converting the solar flux DNI into electricity. And then we have a concentrated solar thermal receiver, which is converting the solar flux into thermal energy, and it can be stored through using molten salts, and then it can be further passed to the heat exchanger, through which we can directly sell the heat to the heat market, or we can use that heat to produce electricity through steam turbine. And then the third receiver we have here is a hydrogen receiver, through which we can have the hydrogen production through in two ways. One could be to use the solar energy and directly doing the methane reformation, biogas reformation here, or the other process could be to use the electricity for doing the methane reformation or the biogas reformation to produce hydrogen. It could be a steam methane reforming, or it could be a dry methane reforming, as Rola has explained. And then we need water, biogas, and CO2 as three commodities to supply to this receiver and produce the hydrogen. So so as we can see in this picture that we have different operations going on at the same time. So what is the objective of designing the operational strategy for these plants? So the idea is to design an optimal operational strategy such that we know at the one particular time instant whether it is good to produce electricity or to share the flux to the solar thermal receiver, and it stores that as a heat, which can be used later during the low sun period, or when we have the high electricity prices. We can use that, or we can use that to produce hydrogen further when we don't have any sun, and at what instant what it is beneficial to produce hydrogen. So all these kind of operational strategies are basically decided by designing a energy management system for these kind of a plant. And the second aspect would be, if we are having these many components in our plant, they are coming with definitely higher investment costs, and also they are coming with their operational cost, because we have to pay for the water we are consuming or biogas we are consuming. So in that instance, it is also required to do some financial evaluations or the economical analysis to identify what are the revenues earned and what were it able to meet up the investments that we have made in this plant. So what all we need to design and operate such SOLARX facility? So the different type of input data is required for this process. So it is first of all, we need to know what is the plant location, we need to know about the energy markets, then the technical parameters of technologies and how they operate, their associated operational cost and investment cost. And what does the individual include is, in terms of plant data, plant location, we need to know the weather profile of that particular location and the price data. For example, electricity prices are different in different parts of the country, of Europe, or like every place have different electricity prices, or they could have different heat prices or hydrogen prices. So in that respect, we need the energy market information, what all markets we have potentially at that particular location and what are the prices associated. In the terms of technical parameters, we need to know what are the characteristics of that technology, what is the efficiency, what is the maximum capacity available, or what could be the optimal capacity that we can have. And while we are modeling a technology, we need to know how it operates, what are the conversion process and equations involved, what are the constraints on the operation of that technology. In terms of operational cost, as I mentioned earlier, there is a associated operation and maintenance cost with each component, and then whatever commodity we are using throughout the process, like water or biogas, there will be some consumption cost associated to it. And investment costs are basically the capital expenditures, which is about the equipment cost or installation cost. So with all this data, we have to calculate the optimal operational strategy of the plant and the corresponding financial KPIs to assess the performance of a plant and to see whether this plant at a particular location is techno-economically feasible or not. So how we are doing it? So we do at D2, we have a tool called High Design, which is a Python-based open source tool. And it's an open source tool, and you can access this tool through this link. And this tool is capable of designing the size of the plant and to design the operation of the utility scale hybrid power plants. And since every component has a different characteristics and different operational behaviors. So it will lead us to have a multidisciplinary optimization problem. So high design is implemented in an open MDAO framework where we can easily combine components which are developed in different environments. And using this tool, either we can do the sizing optimization to know what should be the optimal capacity of my plant, or we can also evaluate the performance of a given plant design. And the objectives could be to minimize the levelized cost of electricity or to maximize the returns over the investment. And the key components that we have modeled in this tool are wind, solar, battery, power to X, and solar. Now we have also added solar to X. So whatever I have explained in the previous slides are modeled in a high design tool and to assess its economical performance. So using this tool, when we have done the techno-economic analysis, so what are the key observations? So basically, we have considered that there is currently no heat market associated with our SOLARX facility, and we have considered the plant is connected to the electricity market, spot market, and the hydrogen market. And we have run the simulations for three locations, one in Denmark, one in Germany, and one in Spain, covering north to south of Europe. So what we have seen is that the economic viability of SOLARX plant under electricity only scenario is limited. We are not able to get more profits just from the electricity market. But if we include the hydrogen production within the same facility, it is much more profitable. And or if we reduce the technology cost, for example, especially for the steam turbines or the thermal storage, which are quite expensive right now, then we could see a more potential in the economical viability of these plant. So this projects that inclusion of hydrogen production enhances the business case for SOLARX, and reduction in technology cost will also favors maybe participation in heat markets, which we are not able to see now that much. And CST receivers, molten salt storage, and these steam turbines, they are mostly preferred in the current scenario, is mostly preferred only for the energy arbitrage. So during the low sun and the peak price periods, they are generally used so that we can do the energy arbitrage during that time. And considering the favorable weather conditions in Spain for specifically SOLARX technology, it has provided the strongest performance in comparison to Denmark and Germany. And we could see higher returns over the investments there and more revenues, and electricity and hydrogen production is more, and the levelized cost of electricity and COVE is also less in Spain in comparison to Denmark and Germany. But having said that, we have some quite challenges, which I think it has been mentioned in one of the previous presentation as well. But the challenges that we see from operation point of view is the higher technology cost that we have, and still there is a limited data on the technology, so the models could not be that highly accurate. We are still in the process of improving the models that we are using for seeing the operations and doing all this financial analysis. That's all from my presentation, and you are welcome to contact me for any questions if you have further. And now I'll give it to Ode. She's a postdoc at DTU, and she's working with the life cycle assessment of these plants. And over to you, Ode.
Yeah, I think that was a great presentation, and I'm excited to kind of complement that with some of the work that I'm doing. Let's see here. So in theory, you should see a screen with sort of 3 layers.
Yes.
Yes, perfect. So now that the audience is, just has a lot of expertise in SOLARX, I figured we could kind of start by kind of flipping the script and starting a bit with the sort of methods that my team brings to the table, and then we'll work and look at how the methods can be applied to SOLARX. So I like to start with this diagram because it's, see if I can change it. It's a bit of an illustration of the UN Sustainable Development Goals. And what's interesting about this is that we have different layers. So we have the economy, the society, as well as the biosphere at the bottom. So the biosphere basically encompasses the natural environment, and the fact that it's at the bottom here is kind of illustrating how this sort of healthy environment can help support a healthy society and a healthy economy. And because of my great co-presenters on this webinar, we've heard a lot about the economy of SOLARX and also how it can benefit society. But here we'll talk more about whether we have good or adverse impacts on the biosphere of SOLARX. And to do that, we're going to use life cycle assessment. So I'm going to give a quick introduction to my DTU section where I work here. So we're about 40 PhDs and postdocs led by 10 staff members. And we're well poised to work on these LCA methods because we've worked a lot on developing and applying them. We've looked at kind of large scale systems, which is exactly what SOLARX it will hopefully be. We also look at the assessment of environmental sustainability in absolute terms. So this means going from better and better systems to ones that are good enough. I won't get into that too much here, but happy to talk about it later. We also work to kind of operationalize these sorts of sustainability recommendations. And the section teaches DTU students across the board through 3 different mandatory classes, really trying to instill what LCA can do and where it can be useful. All right. So life cycle assessment. I'll give you a very quick introduction. That's looking at things from a life cycle perspective. So we start by looking at the whole system, everything from the raw materials extracted to the dismantling and decommissioning stage. So this is really thinking about what the SOLARX system will look like. And then I've spoken to each of the great colleagues on the phone to try to gather life cycle inventory data. So this is input data about, for example, the amounts of materials that are used, or when we're operating SOLARX, what sorts of water or energy needs are there. And so once we have these big tables, which I'm still working on finalizing, we can work in doing a life cycle impact assessment. So these are methods to characterize different environmental problems. So we can translate, for example, megawatts of energy used into carbon or into methane emissions that can then be translated into kilograms of CO2. And these are a lot of different impact indicator scores that address different environmental problems. So I'll loop back to SOLARX now. Sometimes we get the question, why look at SOLARX with LCA? Because LCA is a lot of time and effort, and it really excels when we look at systems that are already established. Well, SOLARX right now is a lot of really innovative technologies that we're trying to bring together and think about where best to establish them. So I'd like to argue that LCA can be a good early warning system for potential issues, and then we can also run calculations to try to address those issues. So this kind of goes hand in hand with some of the work that Mega's doing on making sure that we have a good business case. LCA also incorporates different uncertainties, and we can refine it later. So when we're more and more sure about, for example, which carbon capture technology we're going to use, we can implement that. And LCA itself, as a method, needs a bit of development to better consider the future. So what has kind of comparable LCAs of CPV and CST systems have told us from the past? So they've indicated different potential hotspots. So hotspots are areas where we might have a lot of impacts and want to look into. So the addition of those energy storage technologies, other scholars have found, decreases the impacts because it reduces the grid electricity demand for CPV, sorry. And in CST, those nitrate salts, so what runs into those molten salt tanks, carry heat and had higher impacts. And then also the addition of autonomously operated heliostats, kind of like the work that Marianne presented, has in the past reduced impacts by approximately 10%. So we're interested to see what sorts of innovations and impacts we can have reduced with the exciting work in SOLARX. To complement these sorts of past studies, we also see a need to compare these impacts to other types of renewable energies in the future. So I'll go rather quickly on this because everyone's pretty familiar with SOLARX by now. But in SOLARX, we have our concentrated photovoltaic, we have our concentrated solar thermal, which can produce electricity either at a later time or produce heat, and then we have our hydrogen production. And this kind of produces a basket, we'll say, of SOLARX generated electricity and hydrogen. And in our LCA, we really want to kind of compare that to the basket of electricity and hydrogen that'll be used from the grid. So unfortunately, I don't have any great results to show you just yet, because our LCA remains under development. We're working to gather LCA from each partner, try to scale that to what an industrial plant would look like. And as Megan mentioned, we're also looking at regional differences in proposed SOLARX plants. So we wanted to model a plant in Spain, one in Germany, as well as one in Denmark, because different environmental impacts might matter differently in those places. So for example, in Spain, if we have high water use, it would really be something to look at. Well, in Denmark, we have an abundance of water. And with that, I'll say thank you so much. I'm Aude Bichou, a postdoc here at DTU. Alexis Laurent is the professor that's leading this work. And we're happy to be a part of a set of great colleagues here at SOLARX. With that, I think I'll pass it back to Marta to say a few words and wrap up our session.
Thank you, Aude, and thank you to all of you. I think it's great to see such a great representation of women in science here. And thank you, Rola, for a very good introduction, or very good comment on that as well. And we do actually have a little bit more time for a panel discussion. And we have one question from the audience, and actually it is to you, Rola. Thank you for the insightful presentation. I just wanted to ask a question, as you have used a term negative hydrogen. What is meant by that?
No, I think there was a misunderstanding. What I was meaning to say is carbon negative hydrogen, which means that well, a neutral carbon hydrogen would be that doesn't emit. A negative would be a hydrogen that also removes carbon dioxide from the atmosphere or from the environment. So that's what I meant by it was carbon negative hydrogen, not negative hydrogen. I hope I answered your question.
And the carbon negative hydrogen, I understood that we are doing that also we could be doing that also in SOLARX, correct? So
yes, because if we're using dry air forming, then we're also using carbon dioxide, so it would be removing it from the environment.
Exactly. Thank you. And thank you again to all of you. I think we don't have any more questions in the question window, but you're always welcome to contact all of our presenters. We discussed that before, and we'll be happy to answer your questions. And yes, we hope to see you at the next SOLARX webinar. Miriam and I discussed that there is going to be a next one. And also, if anybody that you know could be interested in this webinar, as Miriam mentioned, we are going to post some highlights of it in our communication channels. And yes, looking forward to the release on the 11th of February, which is the International Women in Science Day. And happy to celebrate it with you today, with all of the great colleagues in the SOLARX team. Thank you.